Let's get started. Okay. So it's my pleasure today to welcome Dr. Lynnae Quick, who's coming up to us from the Smithsonian Air and Space Museum. She's in the Center for Earth and Planetary
Studies.
So I'm blanking on the S there. Actually, I met Lynnae when she was a postdoc over at Goddard, working in the Planetary Geology and Geophysics group. And today she's going to be talking to us about cryovolcanism in the solar system. So I know a lot of you have questions about what are cryovolcanoes and how do we actually study that, and Lynnae's going to tell us all about it. So let's give her a really warm welcome.
All right, thanks so much, Nick. So I'm going to try my best to answer questions about cryovolcanism. What is it? Is it just something we made up? So we'll go through. I promise you it's not, by the way, but we'll go through this. I just want to acknowledge my collaborators who have worked with me on these projects that I'm about to present. Sarah Fagents at the University of Hawaii at Manoa was really one of the first people to look at cryovolcanism on Europa. Herself having a background in volcanology and actually model some of these processes. Also, Lori Glaze and Terry Herford at NASA Goddard, Steve Beloga at Proximy, Ross Beyer at SETI, who gives provides us with topography for some of these features, Louise Proctor at LPI, and also Sierra Ferguson, who is a PhD student at ASU studying Europa. And when she started working with us, she was an intern. And so it's always good to see that as an advisor that you did not kill anyone's spirits so much that they don't want to study Europa. So it makes me feel really good that she's studying Europa. Anywho, so let's get through this. This is the outline. I'm first going to give an introduction to cryovolcanism. What is it? Where do we find it? Then I'm going to talk about my favorite moon in our solar system, Europa, review its physical properties and evidence for cryovolcanism there. And then we're going to talk about the problems with cryovolcanism and how we've kind of overcome those, we think. And the composition of cryolavas. I'm going to present some cryolava dome models. Then think about cryovolcanism as a proxy for habitability. And we're also going to touch on NASA's Europa Clipper mission, which is really exciting. So first off, cryovolcanism. And this is a slide that I have in because a lot of times I give talks on cryovolcanism to groups that are more general or groups who are physics majors, and so I usually have to go through this. I do not have to do that with you guys today, so I will just say that we know that there on Earth we have silicic volcanism, and that depending on the composition of the magma involved, we either get low viscosity, effusive eruptions such as what we see on Hawaii, and these are quiescent, or if we have rhyolitic or dacitic type lava that has a high volatile content, it's high viscosity, we get these explosive eruptions similar to Krakatoa, which is what we see here. And cryovolcanism is no different. When we think about cryovolcanism, we have effusive cryovolcanism, which is when we have surface flows of aqueous fluids. There may be salts, there may be crystals, depending on how many ice crystals there are, the ice crystal content, the viscosity may be such that the rheology is more like a slurry, so that's our effusive eruptions. But we also have explosive eruptions, and this mostly takes the form of geyser-like plumes, similar to what Cassini has shown us on Enceladus, and we'll look at that in a minute. And when we look at eruption temperatures, we're thinking about eruption temperatures between 200 and 273 kelvins. And we know that on Earth, 273 kelvins, or 0 degrees Celsius, is the temperature at which water freezes. But in the outer solar system, this is really hot. The reason being is because these eruptions occur on bodies with temperatures between 40 and 100 kelvins. And so in the outer solar system, at those temperatures, ice behaves very much like bedrock does here on Earth. And so this is why these eruption temperatures, although we consider them cool on Earth, they're hot in the outer solar system. And so we have looked at cryovolcanism and noticed that it's occurred, or it's occurring now on Enceladus, Titan, Triton, Europa, a lot of the Uranian satellites, Ariel and Miranda, possibly on Pluto, and Ceres. And so one thing I just want to highlight is that cryovolcanism is an endogenic process. And if you're looking at it and you're thinking about volcanism, that's a no-brainer. One thing that we've noticed when we've looked at Ceres and looked at some of the processes occurring there is that Ceres is more heavily cratered than we thought it was going to be. And for that reason, we've kind of had some models come up that say, hey, maybe we had a bolide come in, make an impact crater that heated some melt, And now we have, just from impact cratering, we have some sort of cryomagmatic melt that was produced by a bolide. I wouldn't necessarily call that cryomagmatic melt. You may have a fluid, but that's produced by an exogenic process anytime you're talking about an impactor coming in. So we're not talking about this. We're talking about processes where we have maybe subsurface plumbing systems. We already have fluids in the subsurface. So I've given a quick review of cryovolcanism and compared it to silicic volcanism. So let's kind of look at some of the places where we see cryovolcanism. The first time that we saw cryovolcanism was on Neptune's moon Triton, and I promise you that Triton is a full sphere. It's just that the northern hemisphere was in shadow when Voyager 2 took that image. And so Triton has a surface temperature of about 40 kelvins, and when Voyager looked at Triton, it saw these, and these semicircular units are called walled plains. They are 200 to 400 kilometers in diameter, depending on which unit you're looking at. And if we take another close-up look here, what we see is that it looks like we've had some sort of material inflow into these units. You can see that you have kind of a smooth terrain here and kind of rumpled up here. And these are believed to be ammonia lavas. So this is that effusive type of eruption that probably has similar rheology to basaltic lavas here on Earth. But we have also seen explosive eruptions. If you look here, you see these dark streaks. Here we are kind of zooming in. These are actually nitrogen geysers. And these are at the South Pole, of course, and they reach a height of 8 kilometers above the surface. And so this was really exciting. This was the first time we saw a type of volcanism that was not rocky. And so people were very excited about this. And for a while, after Voyager 2 imaged Triton, almost every smooth surface we saw in the solar system, people said, that's cryovolcanism. And we now know that that is not necessarily the case. And so, it was a little disappointing. We looked at other moons, maybe cryovolcanic ended up not being, until 2005, when Cassini sent us these pictures, these beautiful pictures of Enceladus. Enceladus is a moon of Saturn. It's not much bigger than the United Kingdom. Again, a nice sphere. This part is in shadow. And what happened with Enceladus was that Cassini spacecraft was looking at Enceladus and found a localized atmosphere at the South Pole. And the atmosphere was transient. And so what we had was an atmosphere on a body that is way too small to have enough of a gravitational force to hold on to an atmosphere. And again, it's localized, it's transient. Several instruments detected this, and what happened was they went back and looked at it with a camera, and this is what we found. We found these geysers. This is up close. Here is from far away. This is invisible. Here, this is Cassini UVIS, the ultraviolet spectrograph here. And so the geysers are mostly water ice. There's some ammonia. It's pretty exciting because there's evidence for rocky particles, meaning that this material that's geysering out could have some contact with an ocean floor, and so that has all sorts of implications for maybe hydrothermal vents. Once we think about hydrothermal vents, we think about life. So that was really exciting when they found rocky particles. And so these geysers, the larger particles extend up to 500 kilometers above the surface. The vapor and the smaller particles actually feed Saturn's E-ring. They provide water vapor and ice crystals to Saturn's E-ring. So this is pretty cool. So recently, some of us have also been looking at Ceres, which I've called it a hydrous asteroid, but it is our very own dwarf planet in the inner solar system. And Ceres is a little bit warmer. The surface temperature is a little bit higher than the bodies that I've shown before. This is an actual image of Ceres from the Dawn spacecraft. This is actually just a cartoon, as many of you probably already noticed. And what it's showing is this venting. Back in 2014, what was suggested was that we had venting coming from Ceres, and everybody got excited because it was localized. And again, Ceres is too small to have an atmosphere. So everybody thought cryovolcanism, this is really exciting. And so this artist drew this picture, and so the Dawn spacecraft actually went back and looked for evidence of water vapor venting from Ceres, and we have not seen it yet. We haven't seen any evidence of that. But what is interesting is we did find these bright spots on Ceres, and there are about 100 bright spots, but the brightest ones are seen here. This is in a crater called Akator Crater. And what's interesting is the locations of the bright spots match up with the locations where this water vapor venting was detected. And we're still trying to figure out So does that mean that these bright spots were in place by some sort of venting? Did we have fluids come to the surface and maybe boil away because Ceres doesn't have an atmosphere and leave behind these salt deposits? We don't know. Several of us are studying this. We have a special issue that's coming out that's going to be talking about how we think these salts may have gotten to the surface. And so that's more news to come on that. But I think a lot of you will remember that one of the first kind of objects that was imaged by Don that kind of made a splash in the community was that Huna Mons. And so we believe that Huna Mons is a cryovolcanic dome, but it's not just ice and salts. It also probably has a little bit of a mud component, so that makes it a little bit different than some of the other features that we see on these bodies. It's about 4 kilometers high and 20 kilometers wide. And so there's a lot of research now because we want to know, why is this the lonely dome on Ceres? And there's a researcher at LPI, Mike Sorey, that's kind of looked at this and has postulated that there may have been more cryovolcanic domes on Ceres in the past, and they viscously relaxed because Ceres is so warm at 168 Kelvin surface temperature. So that's Ceres. Finally, looking at Pluto, these are images from the New Horizons spacecraft. This heart-shaped region is Tombau Regio. If we kind of zoom in here, what we see here is something that we were really excited about because this was the first time that we actually saw a construct that looked as far as a cryovolcano, that look very similar to some of the volcanoes that we see on Earth. This is Huna Mons. It's about 2.5 kilometers tall. Here is the vent, 150 kilometers wide, and we can see here you have this kind of smooth material. It's believed that you had some sort of cryovolcanic fluid that kind of flowed out. So this is dormant. We don't believe Huna Mons is still active, but it was really exciting because a lot of the other things that I've shown you have been geysers, or in the case of Huna Mons on Ceres, you can't see a vent there. So this was really exciting. So we've talked about cryovolcanism, what it is, where we find it, and we've looked at examples. So let's now get to Europa, which is my very favorite moon, as I mentioned before. So this milky white here is the icy surface of Europa. Europa actually has a water ice shell. You can see that it's extensively fractured. These reddish brown features or stains on the surface are believed to be areas where there was some sort of communication with a subsurface ocean and you had salts and mineral acids deposited on the surface. So to talk a little bit about Europa, Europa has an iron core, silicate mantle, and a hydrosphere that includes a subsurface ocean and an exterior ice shell. And the combined thickness of this hydrosphere is somewhere between 100 to 150 kilometers. We are not quite sure how much of this hydrosphere is ice shell, how much of it is liquid water. We do believe, based on geophysical modeling, that at most the ice shell is about 30 kilometers thick. So that leaves you with anywhere between 70 and 120 kilometer deep ocean. And one thing to note about Europa, we call it an icy moon because it has this icy shell, and all the geology and the geophysical processes we see happening occur in the ice shell. But Europa is actually about 90% rock. And when I was in grad school, one of my professors used to say that Europa is really tricky. It's actually a rocky body masquerading as an icy body. So that's really interesting to think about. Again, we can look at its internal structure. When we look at the size of Europa, here is Europa and compared to Earth's moon and Earth. It's a little bit smaller than our own moon. Acceleration due to gravity pretty low. Very chilly, 100 kelvins on the surface. Different surface species, sodium chloride, sulfate salts, sulfuric acid hydrates. And one thing that's really interesting, about 4 years ago, Simon Kattenhorn and Louise Proctor suggested that Europa may be the only other body in the solar system other than Earth that has plate tectonics. And so that's pretty cool there. And so we'll just look at Europa's place in the Jupiter system. This is a picture of Europa and its sister moons, the Galilean satellites, of course not to scale. You see the Great Red Spot, about 300 Earths would fit into the Great Red Spot. These moons are all significantly smaller than Earth. But what we see here is this kind of triangle here denoting tidal energy. Or tidal heating. And what is that? And basically, what that is as these moons are orbiting Jupiter on their eccentric orbits. So they are, different parts of these moons are pushed and pulled and tugged at different points in their orbits, and this creates friction in just the same way that rubbing your hands past each other on a cold day creates friction. And when you rub your hands past each other on a cold day to create friction, you're going to do that because that generates heat. And so in the same way, this pushing and pulling on these moons creates tidal friction that's dissipated as heat. And so tidal heating or tidal energy really is what determines what geological processes are really dominant on these moons. And so the moons with the most tidal energy or tidal heating have the most interesting geological processes, or the most dynamic, I should say, geological processes occurring. So when we look at Io, it's closest to Jupiter in its orbit. Io is the most volcanically active body in the solar system. If you were to look at it with a telescope, or you were to send a spacecraft there at any time, you'd see hundreds of volcanoes erupting. We're going to skip over Europa, go to Ganymede. Ganymede gets less tidal heating than Io, but it still gets some tidal energy. And so tectonics, not plate tectonics, but just tectonics is what basically resurfaces Ganymede. We have a lot of tectonic structures. By the time we get to Callisto, poor Callisto, Callisto gets basically no tidal heating. And so it has a very pockmarked surface. I don't know if you may not be able to see it too well here, but it has a very pockmarked surface. And so impact cratering is basically what's prevalent on Callisto's surface. When we get to Europa, Europa gets less tidal heating than Io, but significantly more tidal heating than Ganymede. And so it's in a regime where it can have tectonics. We just talked about plate tectonics, and we also see this fracturing here, but it can also have volcanism. And that's pretty cool to think about. And if we go to this next slide, speaking of the tidal energy on Europa and how this affects it, this is just let's see if the movie will work, just kind of showing how when Europa orbits Jupiter, it's pulled and it's pushed and it's flexed, and so that kind of creates some friction. And so again, Europa is in kind of a volcanotectonic regime, volcanism and tectonics. But what is the evidence for cryovolcanism there? And is there evidence? And of course there is, or I would not be here. And so here, what we have is this feature. I've heard it does not have a formal name, I don't believe. I've heard it called the fishing hole. I've heard it called the pond. And what we see is here are the background plains of Europa, rigid plains. You have some craters there. And what you have is, when you look at the pond-like feature, you have this smooth material here. And it looks like what you had was some type of flow that got to the surface and spread in a radial pattern. Just want to point out that this is a small crater. This is not a vent here. So this flow is probably not that thick, because you can still see part of the background plains beneath it. But it's been suggested that maybe this is sulfuric acid that bubbled up onto the surface. The jury is still out on that, but that's been one of the suggestions. This mitten-shaped feature, we call it the mitten. The correct name for it is, or the formal name for it is Murius chaos. And what we think happened was, we think that we had some sort of fluid, kind of, if you will, kind of a diapir of warm ice that just kind of impinged onto the surface and kind of broke through the surface. Maybe some fractures were there, and it was so viscous that it made this type of mitten-like shape. So this would have been maybe lower viscosity. This would have been a little bit more viscous. And this is Thrace macula. And it really doesn't look that interesting on first glance. It looks like it's been baked in the middle. You kind of have this hamburger meat pattern in the middle. And here it is, looking at it close up, still looks like it's been baked in place in the center. But at the edges, we have what we believe are flows, again, flowing onto the background plains, these kind of low albedo units. So that's our effusive cryovolcanism on Europa that's just meandering across the surface, not really bothering anybody. What about explosive cryovolcanism? And again, we have evidence for that. This is a double ridge on Europa, and it doesn't look too exciting at first glance. You see this white arrow kind of pointing to the edges. What is this white arrow pointing to? When we make a close-up view, what we see is all these white arrows are pointing to a low albedo deposit. And it's been suggested that maybe we had some sort of geyser that was erupting from the central trough set here, and it threw salty particles, ice, vapor on ballistic trajectories and kind of lined the ridge. And we believe we could have had a similar process here where we're looking at these kind of freckles on Europa's surface and these other ridges that are outlined in this reddish brown stain that we believe, again, could be mineral acids or salts that were kind of spewed out onto the surface doing a ballistic eruption. And the same thing here, this is Rhadamanthys Lynnae, and again, you have these dark halos, these low albedo spots that these arrows are pointing to. So this is all well and good. So I've showed you effusive cryovolcanism, I've showed you evidence of explosive cryovolcanism, this was nice, and these are very nice pictures that lots of people present. I actually presented them during my dissertation defense, and so it was great. But what we didn't have then was this. So these pictures are from the early 2000s. In 2014, we had this little bit of research come out that really excited us in the Europa community. Again, Lorenz Roth and his group basically were using the Hubble Space Telescope to look at Europa. And we kind of had a similar situation with what happened with Enceladus. So they found excesses in hydrogen and oxygen at the South Pole, just centered at the South Pole. Sometimes the excesses were there, sometimes they weren't. I don't know if you can see this too well. Here's October 1999. You see a little bit of something there, November 2012. Don't really see anything. December 2012, there you go again with these transient excesses in hydrogen and oxygen. And it was suggested then that what we have, again, were geyser-like plumes erupting from the South Pole, full of water vapor, and that's what was producing these excesses. This is what an artist, this is an artist's kind of rendition of what he or she thinks was happening on Europa, and this was really exciting, except for groups kept going back and looking for evidence of this, and they couldn't repeat the observations. They couldn't find observations that suggested that we had this kind of transient atmosphere at the South Pole. Until 2016, I think Bill Sparks' group at Space Telescope kind of went back and looked, and they found evidence of these plumes, not just once, but twice, 2016 and then again last year. So we're pretty confident that we have some sort of geyser-like activity at Europa's South Pole. So in talking about all of this, and in just presenting how these fluids get to the surface, whether it's effusively, whether it's explosively, one question that came up in the Europa community, and one question that a lot of your astute graduate students asked over lunch is, don't we have problems with cryovolcanism because of buoyancy? And this is something that we've thought about. And so 2 issues with cryovolcanism. Again, the first is buoyancy, that we have fluids descending through an ice shell that is much less dense, so these fluids should be negatively buoyant. And then an issue of superheated versus super cooled magma, and I'll get into that in a bit. So we think that we may have solved the buoyancy problem, if we consider that Europa's icy crust was formed by the freezing of a once of an ocean from the top down. We're likely to have brine pockets and other impurities mixed in with the ice, so we may not necessarily have a pure ice shell. And so in that case, the ice shell could be more dense than cryomagnetic fluids. In another case, what we could have is a situation where we have these discrete fluid reservoirs located in the crust. So we don't have fractures that are, instead of having fractures that are linking the surface of Europa to a subsurface ocean that may be 30 kilometers beneath the surface, what we have is these discrete fluid pockets that are at shallow levels in the crust. And what happens is, as these fluid pockets begin to freeze, in this example, excess pressures are created because ice takes up more space than water. And so as they freeze, you have fluid-filled fractures that are produced, and these excess pressures cause fluid to be pushed to the surface. Again, Europa is also experiences lots of tidal heating, lots of tidal stresses. These arrows are meant to represent tidal stresses. And so excess pressures caused by tidal stresses could have kind of squeezed on these discrete fluid pockets too, and also pushed fluids to the surface that way. And Ceres was the first one to actually think about this. So in this case, we think that the buoyancy problem, we can get around that. We can use excess pressures to get these fluids to the surface. What about the case of supercooled versus superheated magma? Just to go through this really quickly, here's pressure temperature diagrams for basalt. For water, I know that they are not right side up. This is the way that I like to look at them, so this is how they are. But what we have is, we know that magma ascends adiabatically, and we know when we have we have an adiabatic system, We know that the temperature changes, but heat is not lost out of the system. And so that makes magma, to simplify it, want to superheat as it's going to the surface. So for this reason, this is why we see so much volcanism on Earth, and we've seen evidence of it on the terrestrial planets. We also know that magma is a multi-component system. So not only do we have just molten rock that can be pushed to the surface, but we also have this mush that may also be pushed to the surface of crystals and molten rock crystals and just different compositions. When we look at water, just a pure water, of course, we don't have that. At 273 kelvins and above, it's liquid. Below, it is solid. And so this creates a problem, because as this watery fluid wants to move to the surface, instead of wanting to superheat like magma does, it wants to freeze. And so how do we prevent that from happening? In much the same way that we prevent our streets from icing over when we have snow and when we have ice, we need to add a de-icer, and that becomes brine. And this is something that was suggested, and when we look at it, we're able to see that you actually make a multi-component system if you are able to add enough brine, and you get a little bit of a mush zone, and you have depressed the freezing point. So you have these fluids that are moving to the surface, again, because of the freezing point has been depressed. They are able to arrive at the surface and erupt without freezing first. So that's all well and good to kind of throw this together and say, hey, the easy way to combat freezing of aqueous solutions is just to add a lot of salt. But is there evidence that fluids that come from Europa's subsurface have a lot of salts? I've showed you a lot of pictures and I've said that they're salt, but what's the evidence? Jim Shirley and his group kind of tackled this in 2010, and basically this is our Gad-Nal regio on Europa, and here's visible, here's data from the Galileo spacecraft's near-infrared mapping spectrometer. And basically what they did was map different regions in our Gad-Nal regio. Well, they mapped our Gad-Nal regio and mapped these. We look at low albedo plains, we look at other surface units where we believe that there has been some contact with subsurface fluids. You find that not only is there water ice, but you have lots of freezing point depressants, sulfuric acid hydrate, magnesium and sodium sulfate salts, magnesium sulfate brine, and that the percentage of these contaminants is quite high. And so this is really evidence that anywhere that we have regions where we think there's been some sort of communication with fluid being brought from the subsurface to the surface, they are likely to be high in salt. So that gives us lots of hope that we have solved the problem of supercooled versus superheated magma, and we solved the problem of these cryomagmas wanting to freeze on the way to the surface. They are likely to be somewhat salt logged. So then, with that being said, we want to ask a question here. And so we've shown that there's evidence for cryovolcanism on Europa. We've shown that cryovolcanism can happen. We can get these fluids to the surface. And so if certain features on Europa are created by the extrusion of viscous cryolavas, what rheologies are necessary for icy volcanic domes to form on Europa? And these are some of the models that we're developing. So we're actually looking for cryolava domes. And when it comes to cryolava domes, what are we talking about? We're just talking about a subset of domes on Europa. There are lots of domes on Europa, but we're just talking about a subset of them that we think could have been produced by cryolavas erupting onto the surface. They're very viscous, they expanded radially and form these dome-like shapes. And these domes are roughly circular to elliptical features. They may be surrounded by low albedo moats, as you see here, and they don't mimic the character of the surrounding terrain. That's really important. It doesn't look like there's just been some sort of something that's impinged on the surrounding terrain and punched it up to form a dome. It actually looks quite different than the background planes. And so we've talked about how these fluids may get to the surface to form these domes. Here are some examples of other domes on Europa that we believe were produced cryovolcanically. They are generally 40 to 100 meters in thickness or in height. They are 3 to 10 kilometers in diameter. This makes them intermediate in size between volcanic domes on Earth and volcanic domes on Venus, but they are thought to have formed in the same way. Seraph agents, who I mentioned earlier, actually modeled the formation of these domes using models that have been applied to domes on Earth and Venus. And so she did that in the early 2000s. And what we wanted to do was take a second look, work with Sarah and take a second look at this. And here's some math. I will go through this really quickly so it's not as painful as it looks like. So basically what we have is Hubbard back in the early 80s found similarity solutions for the radial spreading of a viscous fluid on a surface. And he applied these solutions, he and his group, to the formation of volcanic domes on Earth and Venus. And that hadn't been done before. The issue with the application of this is that these similarity solutions, when you try to run the models, it produced an infinite flow rate at the vent. And that's something that you don't want. You don't want there to be an infinite blob of lava at the vent. That's never good. And so what we've done is we looked at what Hubbard did, and we explored an alternative form of the diffusion equation that describes the radial spreading of a viscous fluid on the surface. And before I get into these equations, what we have essentially assumed here is that we have a blob of cryolava or a blob of slush, whatever you want to call it, that has just been instantaneously plopped onto the surface. And what we do is we watch it advance radially and relax vertically. So it kind of flattens out and advances into a dome-like shape. And that's the way the model goes. So we have this diffusion equation. H is the thickness of the blob. Theta is a time transformation constant that includes a time-dependent viscosity. This was something that wasn't done in the earlier models. Why is a time-dependent viscosity important? Because as this cryolava sits on the surface, it is going to cool. It is going to, as it cools, it's going to become more viscous. So we have a time-dependent viscosity. G is our acceleration due to gravity on Europa. Nu naught is our initial kinematic viscosity, and R is the radial distance. So we have this equation describing the diffusion of a fluid. Here's the solution to the equation. And it allows us, using this solution, to plot dome profiles. Here's thickness again as a function of radius and time. We have our volume of the blob, we have a time transformation constant, we have gamma, which I'm going to show you on the next slide, is a time scale over which the viscosity of this blob increases exponentially. And so with this equation again, thickness as a function of radial distance and time, we are able to obtain dome height as a function of radial distance from the origin at multiple time steps. So here with that equation, we are watching our blob again advance radially and kind of squish vertically into a dome-like shape. So we've instantaneously plopped it onto the surface. After 4.4 days, there isn't much movement. This is an axisymmetric plot, by the way, so mirror image would be plotted here. So after 4.4 days, not much movement. 55 days, a little bit movement, 7 months, a little bit more. After 3 years, what we find is, when the model comes to a stop after 3 years, what we have is a dome with a radius of 2.5 kilometers and a height of about 80 meters. And this was really exciting because this aspect ratio is similar to the aspect ratio of these domes on Europa. This is assuming a constant, not a constant, but an initial viscosity of 10 to the 7 meters squared per second, and that the viscosity increased exponentially every 7 months. And so this is great. The aspect ratio is similar to these domes on Europa that we believe are cryolava domes, but this is math and it's theory, and we know with math and theory we can basically prove anything. We can suggest that maybe we should all be sitting on the ceiling. So how does this stack up against actual observation? And so this dome here is this dome here, this dome here, this dome here. And so if we take this dome, and this red box is the right side of it, and we plot it, this is the topography gained from the data taken from the Galileo spacecraft. And we can plot it on top and see how it compares to our plot after 3 years. And it's consistent, but as you can see, it's not perfect. And what this says is that we need to consider some different parameters. We may need to assume that we have a higher initial viscosity. We may need to assume that cooling happens more quickly. Again, we have the situation where we've just plopped a blob of cryolava onto the surface, and that may be a problem. And so we'll get into that in a little bit. And so one thing to think about that I just want to kind of touch on here is that when cryolavas are plopped onto a surface, there's no atmosphere here on Europa. Initially, what's going to happen is that they're going to boil violently because aqueous solutions have a very low vapor pressure. And so this boiling is going to commence until we have this outer skin or this kind of brittle icy carapace that forms the top of the flow and is able to insulate it. And so knowing that, one thing that we were concerned with is, well, you could plop fluid onto Europa's surface, and if it's not going to boil away, but initially it's going to boil away. At some point, it's going to have this icy skin. But wouldn't this brittle, icy kind of cover prevent it from moving? And that's something that we looked at and something that we were very concerned about. And so one thing that I just want to mention is that when we consider the low eutectic contaminants such as sulfate salts, sulfuric acid hydrates, they drive eutectic temperatures down to about 200 kelvins, or the freezing temperatures down to about 200 kelvins. And we know from laboratory work of brines that brines may reach 5 to 15 degrees before their actual freezing temperature before crystallization occurs. So basically, what we wanted to do was we wanted to plot the flow and get its temperature at a bunch of different times. Remember, T is equal to 3 years as the time it took to form our original dome. So we wanted to see, after 3 years, what was the temperature of this lava. And so for an 80-meter thick dome, what we found, depth into the flow, temperature, time, after 3 years, which is how long it took for us to form our dome, after 3 years, only the top 10 meters fell below the 200 meters freezing temperature. So only the top 10 meters would have become brittle. So in that case, if we have the top 10 meters are brittle and we have a liquid core that's still a little bit warm, we believe that the flow should still remain mobile, even with this icy crust atop of it, should still be able to advance and relax to form the dome. And so we're not so naive to think that this outer cryolava crust won't provide a resistive force to dome formation at will. But similar to the case for silicic lavas, what we think is going to happen is that the hydrostatic pressure of this liquid beneath the skin will initially be large enough to overcome that pressure and entrain the crust as it moves along, as the flow moves along. The net effect of the skin is to increase the apparent bulk viscosity of the fluid by 2 to 4 orders of magnitude. And so that's something that we have to keep in mind when we're modeling this. So to review, we've modeled flows of a fixed volume. We've assumed that we have just a constant volume slush blob that's just plopped onto the surface. And we found that cryolava domes could have been formed by cryolavas with bulk kinematic viscosities of 10 to the 7 meters squared per second. That's including the brittle crust. When we consider the actual viscosity of the fluid cryolava, the initial viscosity is probably much lower. And so one of the big problems here that I've highlighted here is that we've considered dome emplacement, again, for a fixed cryolava volume. We've just drop slush onto the surface, but that's not realistic, and it provides no insight into how this cryolava got onto the surface. And so we need to consider dome formation and relaxation when we have cryolava or when we have slush that's actively erupting onto the surface. And that's what we're doing now. So we have what we call a volume flux approach, where we assume we have a constant flux of lava that's being erupted onto the surface. And we've applied it to the formation of steep-sided domes or pancake domes on planet Venus. And so now what we want to do is apply it to the formation of these domes and similar domes on Europa. Here again is our diffusion equation. Note here that U is the velocity of the lava, and here we have N, which allows us to assume a certain rheology. Here we've assumed a Newtonian fluid for simplicity. Here's the solution to this equation. Note that Q here is the volume flux, which shows that it's erupting. We have a lot of constants here, but what we need to show is that we have a perturbation solution to this diffusion equation, and we are able to once again plot flow thickness profiles of dome thickness as a function of radial distance for different times. And so what we find here is when we assume that we have a constant volume of cryolava erupting from the vent, if we assume a somewhat lower viscosity of the cryolava, about maybe 10 to the 4 meters squared per second, and we assume a constant volume flux of 275 meters cubed per second, what we find is that after just 40 days, we are able to produce a profile that matches the aspect ratio of these domes. Again, 80 meters thick, 2.5 kilometers wide, I'm sorry, 2.5 kilometers in radius. This matches the aspect ratio of these domes. Note that when we were just considering a blob of fluid that relaxed, it took about 3 years to form this. Here we're forming it in about 40 days. We're also able to start the model much closer to the vent at just, start the model with an initial radial distance of 10 meters. And again, how does this match up with topography? Here is this dome here, for example. The red box is what we are plotting. Here it is on top of our model. Again, consistent, but not perfect, which is fine. We're still working on these models. This has been funded by NASA to continue this work. And so this is where we are, trying to make sure that our models match up with actually observational data. But the good thing about using this model where we have flow erupting and domes forming instead of just using a model where you have cryolava that's just plopped onto the surface is that we're able to better constrain cryolava rheology, so emplacement time and its viscosity. And one thing about this plot is that we can make a similar plot using several different viscosities. However, there are certain properties of different viscosities that make them unlikely for these cryolavas. First, if we use this was our viscosity that we used 10 to the 4 to get this plot here. But if we go an order of magnitude less and we have a viscosity, a kinematic viscosity that's 10 to the 3rd meters cubed per second, this is implausible. Why? Because it assumes that the dome would form in about 4 days. That's implausible because when we are forming this crust, it can take the insulating crust that prevents the boiling. It can take about 7.5 days for that crust to form. Also, look at this volume flux on the order of 10 to the 3 meters cubed per second. It's representative of eruptions that are much more voluminous, than those required to form domes. Lionel Wilson and Jim Head showed that back in the late 90s. If we look at even higher emplacement times, about 4,064 days, which is greater than 10 years. This is assuming a viscosity of about 5 times 10 to the 6 meters squared per second. That's also unlikely. Why? Because it would require fracture on Europa to remain open with a constant supply of fluid for over a decade. We are not sure if stresses in the ice shell of Europa would support that. Also, the dome material would have to remain fluid for far longer than may be possible, and entrainment of this icy carapace that kind of insulates the flow may not be possible for that long. So what we're looking at is a case where viscosities probably lie in the range of 10 to the 4 meters squared per second, maybe 10 to the 5 meters squared per second. That gives a 40 to a 400 day emplacement times. And it gives advance rates for these cryolavas that are similar to advance rates for terrestrial basalts. Not too much different if we assume the rheologies are the same, and the combination of the volume flux and time produces volumes of lava on the surface that are commensurate with volumes previously estimated for these domes. And so those are our models. That's what we're working on. So we're going to continue to work on these, trying to get observational data to match this theory. One thing you may have noticed that I just want to touch on is that, again, we have these low albedo motes around these domes. Where did they come from? That's also one thing we're looking at. And so maybe it came from co-extrusion. Maybe you had cryolavas with 2 distinct compositions and rheologies and viscosities, that kind of float up to the surface in a fracture side by side. Or it could be due to flexure in certain cases. So these albedo variations in certain cases may not be fluids at all. They could just be flexure on the surface due to the load of a dome forming lava, and that's something that I've been looking at with Terry Herford. So for this model, here are our conclusions and future work. So we've considered dome formation and relaxation when lava is erupting onto the surface at a constant rate. We find that the most likely rheology for cryolavas that may have formed these domes are 10 to the 4 to 10 to the 5 meters squared per second. That's kinematic viscosity. We're going to explore the formation of motes, looking at co-extrusion and flexure. What we want to do is continue to investigate possible ties to the state of the ice shell and processes occurring in Europa's shallow subsurface to the formation of these domes. And high resolution images of the surface and better topography are needed. One of the issues is that we have topography for some features on Europa, but there's a lot of topography that's missing. And so in order to make the models as accurate as possible, we need better images and better topography. And that is where the Europa Clipper mission comes in. And so Clipper is going to launch in the 2020s. So it's 2018 now, so that's the next decade. It's pretty quick for a planetary mission, pretty quick turnaround, and we're excited about that. The goal of Clipper is to explore Europa to investigate its habitability. It's going to characterize the ice shell in the ocean. It's going to characterize once and for all and determine how thick this ice shell is. And it's going to find any subsurface water. If we do have melt lenses in the crust that I talked about, these discrete fluid pockets, it's going to find that. It's going to look at the composition and the habitability of the ocean, continue to look at the composition of the surface, and this is the big one here, understand the formation of surface features, which is what we're modeling here, including sites of recent or current activity, places where there's cryovolcanism. Also, not just assuming that we had fluids erupting onto the surface, but looking for geysers. That's one thing we're going to do. This is our payload, lots of interesting instruments. We have a mass spectrometer, a dust analyzer, so that if we do see a plume erupting, we can kind of determine what the composition of it is. We have Ethemus, which is a thermal imager. It's going to look for hot spots. And by hot, I mean, again, between 200 kelvins and 273 kelvins. A magnetometer. We have Reason, which is our ice penetrating radar that's going to look for horizons in the ice shell, where the shell ends, where the ocean begins. Also look for those brine pockets or those discrete liquid reservoirs. We have the Europa imaging system, which is a dual camera imaging system, a narrow angle camera and a wide angle camera. The narrow angle camera is going to get nice global imagery of Europa. Again, it's going to look for plumes. Highest resolution is about 0.5 meter per pixel. And so let's talk about ice for a minute. This is Marguerite Bay in Antarctica, and this is at 0.5 meter per pixel, I believe. This is the resolution that we hope to be able to see with ice on Europa. So this is really good. This will really help our models. This is 6 meters per pixel from the Galileo spacecraft. This is the best resolution that we have on Europa now. Basically, what I have heard those who worked on the Galileo spacecraft back in the late 90s and early 2000s say is that we have 6 meter per pixel imagery, but it's just postage stamp size. We don't have a lot. Most of the surface is not at this high resolution. So this is the resolution that we're looking for. And the narrow angle camera is going to get us that. One thing that will also help with the topography, remember I said we don't have much topography. This is a little bit of topography that we have. I think maybe Paul Schenck was probably maybe instrumental in producing this, but here's a double ridge on Europa. This interesting shape right here, this darker feature is called the sickle. It's sickle shaped. And so here it is in 3D. And what Clipper is going to get with our wide angle camera is it's going to get a large portion of the surface in 3D so that we have topography. It's going to do that by stereo image pairs. And so that's something that we're really excited about. It's going to be great once we launch. All right, and so let's just look here and kind of think about the astrobiological significance of icy moons after I've gone through all that and just very quickly went through what Clipper is going to look for. And so notice that Europa was about 10% ice, it's 90% rock. By the time you get to some of the moons around Saturn and some of the Uranian moons, you're getting to almost 100% ice. So icy moons can be anywhere between 10% to 95% ice. And so, like Europa, have water ice surfaces and several contain subsurface oceans that may be in direct contact with the rocky mantle. Because of that, we think that we have similar constructs and processes as on Earth's ocean floor, so we may have hydrothermal vents. We know that water may be cycled from the interior to the surface by various processes. I've talked about cryovolcanism here. Impact cratering may also cycle some water in certain ways. In the case of Europa, we have plate tectonics that's going to cycle these fluids. These moons are tidally heated in the case of Europa and Enceladus owing to their proximity to their parent planet. And there could be organic compounds. It's been suggested by some of the geochemists that on the ocean floor, you could have had some organic compounds on Europa. Also, if you have hydrocarbons on the surface, if they were ever able to get to the surface, what you might have is irradiation might take over and you might be able to produce some simple alcohol. So basically we have organic compounds, we have energy, we have water. So So these moons are really exciting because they contain all the necessary ingredients that astrobiologists say that we need for life. So they're very astrobiologically significant. One thing that's also interesting to think about that I've been thinking about with colleagues at the Planetary Science Institute is that cryovolcanism could be it could be an indicator of the habitability of exoplanets. TESS just launched, I think, a couple of days ago. We are going to launch JWST in 2 years, I think. So these are next generation space telescopes, and they are going to find smaller planets. They are going to want to characterize these planets and find out if there could be life. Well, we know when it comes to Europa, when it comes to Enceladus, when it even comes to Triton, that every moon in our solar system that has this explosive cryovolcanism in the form of geysers either has a subsurface ocean or some sort of subsurface liquid pockets. And so if these instruments, if TESS, if JWST could detect explosive cryovolcanism on these exoplanets, that may be a way to kind of, indirect way to kind of infer they may actually have subsurface water. There may actually be habitable environments. So that's something interesting, and that's something that several of us have been thinking about. One thing that I just want to mention here, just give a plug for our workshop. It's going to take place at the Lunar and Planetary Institute in June, Cryovolcanism in the Solar System. If you've noticed, I said that the first time we laid eyes on cryovolcanism was in 1989. That's relatively brand spanking new, so we're still trying to learn about this process, how it works. We want to learn about the composition, more of the composition of these magmas, their rheology, the subsurface plumbing systems, laboratory work and field analogs. We tried to get everybody together who's studied these processes. And so we'd like to see your faces there. We'd like to see people broadly contribute to the discussion saying, this makes sense, this doesn't make sense. What are you thinking? You guys are crazy. Or what we hope we get is, these are good ideas, so keep doing this work. So what I'm going to do is I'm going to leave my conclusions and future work up there, and I am going to take questions if people are still awake and have them. Thank you.
So Europa, it doesn't have a magnetic field.
Europa has an induced magnetic field. So you have salty water and it's spinning quickly, so it's creating a current, and then that creates, that creates a magnetic field that way.
How much radiation have people modeled how much radiation gets into the ocean? Would it be bad for life?
So I know that people are looking at radiation, and I'm not sure anybody's actually looked at how much would get into the ocean. I'm thinking that people have just looked at the surface and assumed that the ocean would basically be safe because you have maybe up to 30 kilometers of ice. So I don't think that people have actually looked at it in the ocean. That's a good question. I'm kind of now wondering, would that make a difference for planetary protection? I don't think people have thought about the ocean. I don't think.
I have a question followed by an observation and another question.
Sure.
What's the atmosphere like?
No atmosphere.
None whatsoever.
No, okay. So there's an exosphere, and some people say that's an atmosphere, but I consider Europa to be atmosphereless.
Okay. So I look at the surface and I see all this red staining, and I think that's iron. I think that you had an anoxic ocean filled with ferrous iron, and maybe it's getting oxidized as it reaches the surface somehow.
The ferrous iron?
Well, it becomes ferric iron, which is very insoluble. And I'm wondering, could that have an effect on the viscosity of your solutions coming up?
If that happened, I think it could have an effect on the viscosity. I have to be honest, I haven't actually thought about that. We basically just looked at the reddish stains on the surface, and we've looked at the spectra we have from NIMS, the near-infrared mapping spectrometer from Galileo, that's shown that for the most part, it's salts, mineral acids that have become irradiated. So I don't think we've actually thought about ferrous iron at all. But that's something to think about.
I look at Europa as an analog for snowball Earth, and so I think of an iron-rich ocean.
That's interesting. That's interesting. I want to talk with you more about that. That's interesting. Yes. Did you?
Okay, go ahead.
Well, the observation was the iron, and then I wanted to know whether that would affect the viscosity.
So Io is sitting there spraying out lots of stuff, and
Yes.
a lot of it lands on Europa, and a lot of it's sulfur and sodium. How do you quantify what you see on the surface of Europa as what's coming up from beneath or what's falling down from above?
What's exogenic versus what's endogenic? That's a really good question. And there are people who actually do spend their time figuring out what is. I don't think that I can answer that personally. As far as how do you quantify what the number, what the amount of material is that's exogenic versus what's endogenic. But the thinking is that the vast majority of it is endogenic. I'm sorry, I'm not able to give you a better answer than that. But you could have material exchange. We don't necessarily think it's to the point where you have a significant amount of material on the surface that comes from Io.
So there's this theory about plate tectonics and subduction. Do cryovolcanism happen to occur where they think subduction might be happening, like how we get arc volcanism? Is there any evidence of that, or is it kind of just weird?
There is. There is. And I don't know if I have, probably do not have that slide here now. I've pretty much gotten out of my show. So there is evidence. There's actually, I know you know the paper Cat and Horn and Proctor, and they actually have a cartoon of the subsumption process, and then they have cryolavas coming up in the areas that you're asking about. And so they do actually see observational evidence of things that look like fluids that have erupted onto the surface at those locations. I don't remember the exact Latin lawn, but I think if you look at that paper, it'll show you.
So in your simple, your example that you had, the second one, you showed the observed versus model, and I couldn't help but notice that the observed would have a much larger volume than your models. And I'm just wondering, is that really rheology that's controlling that, or is it the rate of diffusion, and how do you test which parameter is controlling?
Great question. I think this is what you were asking
yeah,
about.
This has it, but also your second one, the observations are above every one of your times.
There?
Yeah.
Is that there? And your question was, could it be rheology, or could it be that we just have a larger volume?
Well, I guess I'm wondering,
out.
because right now your calculations, the volume of your dome is less than the observed.
Right. And
is that really caused by rheology, or is that just like the rate that you're diffusing ice in your model?
It could be either or, and you make a good point that I mentioned that we have to make changes to viscosity and cooling time. But it could be that we have to play with the volumes that we are letting come out too. And note that here, which I kind of skipped over, this is this dome here. If we were to take our red box and do it for this dome, if we were to take our red box and kind of plot for this dome here, which is this one, we might get something a little bit different. So, but that very good point and absolutely correct.
So we're talking a bit about the astrobiology implications for this. And so if the structure of your domes, they seem to have this hard shell on the outside with a sort of a mushy 200 Kelvin material on the inside, do you think that some of these in-place domes could be a good place to search for biosignatures?
They could be. There was a paper in 2003 by a researcher named Javier Ruiz that suggested that some of the fluids that come to the surface to form these domes would be good transient habitable environments. So that's not necessarily something that I thought about, but people have thought about that. Now, again, this would be probably short-lived because these are compared to the ocean and just the surface area of Europa, these are pretty small, but that hasn't been out of the realm of the possibility as far as papers that have been published and thought about astrobiology on Europa.
So earlier you mentioned there's a very strong tidal force. I was just wondering if that will influence the spatial distribution or local concentration of the domes or cryovolcanoes.
There's a possibility that it could. We found that when we are looking at geyser-like eruptions on Enceladus, for example, so tidal forces do affect when the geysers turn off, when they turn on, and may be affecting where they're all located in the South Pole, but where actually in the South Pole they're actually erupting. So that's a possibility. That's not something that I'm considering here, but it is possible. In addition, a lot of times when we have fluids moving up to the surface, tidal heating kind of can concentrate itself in some of these warmer fluid blobs. So yes, there's probably, although I'm not looking at that, there's probably some link to that.
I'm wondering, is there any, what's the range of the size distribution?
Is there, I'm sorry?
The range of your size distribution.
Mm-hmm.
Some mosaics seem to show that the sizes vary of the dome, right?
Mm-hmm. Mm-hmm.
But I'm not sure how much is the variation, and if there is a variation, then is the height to base ratio change or the shape?
I think Michael Manga at Berkeley and one of his students actually did a paper where they looked at the different sizes of domes and their aspect ratios, at least based on the data from the Galileo spacecraft. They did look at that. So that has been looked at, that has been considered, and probably something that we should think about for our models. Did that answer your question?
Yeah.
Yeah, okay, okay.
I have a really dumb question. For Europa, you said there's a lot of rock in Europa.
Mm-hmm.
So how do you know this is ice?
Well, so you can send we send an instrument to it, and we have the near infrared mapping spectrometer that tells us that, you know, the way that these things work is that ice absorbs at certain wavelengths, and we see those absorptions as far as the surface of Europa, and then we see changes in the absorptions when we have salts. If we're looking for silicates or phyllosilicates, that produces kind of a different spectrum. So.
Could gas be at least a partial driving force for the cryovolcanism? For example, if water is reacting with iron in the core and producing hydrogen gas that can accumulate at the high point of the ocean and generate pressure?
We think that gas plays a role. I'm not sure if it plays the role specifically that you just mentioned, but definitely gas plays a role, and this was kind of something in an effort to not belabor it. I kind of glazed past this one, but this is the case where you have a fracture extending down to a fluid pocket that is very volatile rich, and so when these fluids get to the surface, they're very volatile rich. You're going to have volatile exsolution. That's going to drive ballistic eruptions, and you may have some liquid brought to the surface that just kind of rides along with that. So yes, gas could play a very important role. I'm not sure about with the mechanism you specifically asked about with the hydrogen.
Well, that
but
was just speculating as one
yeah.
possible way to produce gas.
Mm-hmm. Oh, produce gas. Oh, okay. I see. I didn't get your question. Okay. Okay. Interesting.
I have a question.
Mm-hmm.
So in basaltic lava flows on Earth, especially at Hawaii and other places, it's very low viscosity. And you see this process of inflation of a flow where it basically grows in size, and then you can get outbursts that sort of allow the flow to move forward. Are we going to see inflation in cryovolcanoes, or would that help modify the flows?
So I think Ralph Lorenz suggested that for maybe cryolavas on Titan. He started looking at possible different rheologies, and he looked at not necessarily anything that looked like Pohoihoi toes, but what he did look at is the formation of kind of like pillow-like lavas, which there is some inflation involved in that too. Now that was back in the late 90s. That was before we had ever sent Cassini to Titan, and before we were actually able to look at the fluids there. And I don't know if any of us have revisited that. But I think it's definitely possible, especially if you have higher viscosity cryolavas that have a larger ice crystal content. You might kind of get some inflation.
Are there any other questions? If not, let's thank Lynnae and
Thank you.